In this lecture, we want to discuss complex matrices and the forms of complex matrices. So this is going to be very similar to when we discussed symmetric, skew-symmetric, and orthogonal, but it's possible to have in a matrix elements that are complex numbers. So first, a little definition. So when we have the bold A with the bar over it, then that just means if we had some matrix A that had elements A, JK, where JK refer to row column, then we can take the complex conjugate of that matrix by replacing each element of the matrix with its complex conjugate. So if a value of AJK was some alpha plus I beta, where alpha and beta are real, then the complex conjugate of that element would be alpha minus I beta. Also, we can take the transpose of the complex conjugate, and that is referred to as the conjugate transpose of the matrix A. So hopefully you'll recognize this bar notation as being a complex conjugate. So that brings us then to some definitions that, as I said, are analogous to symmetric, skew-symmetric, and orthogonal, and that is Hermitian, skew-Hermitian, and unitary. So a square matrix is Hermitian if its transpose conjugate is equal to the original matrix. So in other words, if each element, its complex conjugate is equal to the original element. It's skew Hermitian if its transpose conjugate is equal to minus A, and is referred to as unitary if its transverse or transpose conjugate is equal to its inverse. So these are the three definitions. Now, these are actually general definitions. They generalize the definitions of symmetric, skew-symmetric, and orthogonal into the complex space. So it's interesting to talk about the eigenvalues of a Hermitian matrix and a skew-Hermitian matrix. Basically, the eigenvalues of a Hermitian matrix are real, and same for a symmetric matrix, whereas the eigenvalues of a skew-Hermitian matrix are imaginary or zero. And so that's the same for skew-symmetric, skew-Hermitian. The theorem applies to both. And then finally, the eigenvalues of a unitary matrix, and therefore an orthogonal matrix, will have an absolute value of 1. So once again, remember that it's absolute value or magnitude, not the number 1. All right, just like with the real matrices, a unitary transformation with a unitary matrix A will also preserve the value of the inner product and also the norm of the matrix. So that's another important thing to know about unitary systems. So basically, what is a unitary system? It's a set of complex vectors that satisfy the following relationships, where the element in a given row and a given column, their inner product is zero, or sorry, a row and a column, the inner product is 0 if j and k are not equal. It's 1 if j and k are equal. So if we took a set of row vectors and we took the jth row and the kth row and we took their dot product, then it would be 0 if they were not the same row, and it would be 1 if they were the same row. So that's really all that means, is that it's very, very analogous to orthogonal. It's just called unitary because it's a complex system. A complex square matrix is unitary, by the way, if and only if its column vectors and its row vectors form a unitary system. So here are just some examples of Hermitian, skew-Hermitian, and unitary matrices. And just like with the matrices in the previous section, where we had symmetric, skew-symmetric, and orthogonal, we basically do the proof by checking the transpose conjugate with the original matrix and see if the following statements are true. And if they are, then that's the category under which the matrix falls. Now, it's important to say, and I probably should have said this in the previous lecture, that not all complex matrices are Hermitian, skew-Hermitian, or unitary. So it's not like a given matrix has to fall into one of these categories. It can be completely none of the above. So that's an important point for me to make. The same is true with real number matrices. All right, the determinant of a unitary matrix, the absolute value of the determinant is equal to 1. And then another important theorem is that a Hermitian, a skew Hermitian, or a unitary matrix is going to have an eigenvector basis that is a unitary system. We're not talking a great deal about eigenvectors in this particular class, given that it's the summer and it's a slightly more complicated topic, but it's an important thing for in the future should you ever do anything like image processing or anything where you utilize pattern recognition, where you utilize eigenvectors. It's important to understand what they are and what some of their properties are. So, short lecture in this video just to go over the basic definitions of what happens when you generalize a matrix with real numbers and allow the elements to become